All right, so recording is officially rolling. So it's Wednesday. You guys just saw a few warm-up Paul Hewitt videos from Linear Motion. I want to take you guys over the story of three match formulas that your day is going to use over and over. It's going to be useful throughout the entire class. Okay, take you guys through some graphs, and for these two different scenarios, that is pretty close to the end class. More stuff we want to do, but another day. Okay. So you guys might remember yesterday, after finishing the car and ramp lab, we started thinking, what variables govern motion? Okay. You guys saw that the mass of the car ended up canceling out, so we're going to put that one to the side, and that'll come back in the future. But for now, we're essentially focused on these five variables. And I like this as a mnemonic device called TAX-VV. We got time, acceleration, displacement. These all have units, right? Seconds. We skip this one, come back to it. Displacement could be in meters. Okay. Now velocity, well, if something's changing velocity, it can have lots of different velocities. So all I care about for solving many problems is what's the starting velocity, that's initial velocity, meters per second. And then at the end of that time interval, let's say 3 seconds tick off, something like that. The final, what we call final velocity, the velocity at the end. Okay. And if the velocity is changing, does it say that these two numbers are different? Well, there must have been some rate change to get from one to the other, and that's called acceleration. That's some number of meters per second per passing second, like meters per second. Combine the seconds, you get meters per second squared. Okay? Which that you should already look familiar. Because yesterday, you guys had a graph, x versus t squared. Remember that slope was centimeters per second squared? Right? Looks a lot like that, right? Technically, you guys found half of the acceleration, but that might make sense by the end of class today, why that would be the case. Okay? Then, how are these five variables connected together? I bet we need some equations, right? I think we need some equations. I'm actually going to start with this one right here to build one of them. So the definition of acceleration is the rate change of velocity. So final velocity minus initial velocity per the time interval it took to change. Right? That is the rate change of velocity. You guys see that? Rate change of velocity. Okay. I'll spell that out. Rate change of velocity. Okay. All right. Now, what are we going to do? I'm just going to rearrange this algebraically. Can you guys rearrange that algebraically and solve for final velocity? You guys can do that? Okay. I'll do that. You guys do that. See if you can stay a step ahead of me. If you can stay a step ahead of me, and this will be a theme throughout this entire year, if you can never stay a step ahead of me, then that means that you definitely know what's going on. And if not, then you know that you haven't quite learned yet. Okay. Cross multiply up to t. So a times t would be the acquired velocity, right? The change velocity. And if I add the v naught over, then I'll swap both sides while I'm at it. I get something looks like this. Final velocity is equal to initial velocity plus acceleration times time. Okay. Box this in. This is one of your three important kinematic formulas. Okay. And then the poster that's hanging front of the room, it's this middle one right here. It's this. So velocity takes up to is equal to the starting velocity plus a times t. You guys see what that one? Okay. All right. Next idea. All right. We're going to piece together a distance formula, or I should say displacement, really. Okay. So tell you guys a story. Let's say you guys are driving on I-95 and you're going north straight towards Jacksonville, and you're on cruise control, and you're looking at 70 miles an hour. Okay, you guys see that? See that? Speedometer says 70 miles an hour. Right. You look off to the side of the road, you see one of those green signs that says Jacksonville is 140 miles away. Who can tell me how long it's going to take to get to Jacksonville? 2 hours, right? Did you guys just in your head basically do this? Right? You said, okay, well, I know it's 70 miles per hour, 140 miles I gotta go, it's gonna take me 2 hours to get there. That's what you guys just did, right? Oh, you guys know that. Right? Now that's only true at acceleration is 0 meters per second squared. That's to say a constant velocity. Constant velocity. Right? As long as you keep going cruise control. I mean, you aren't speeding up the whole way there. Like, gotta hit 88 miles an hour. No, you're just constant, right? Okay. Right. No, so that's part of what's going on. Then you guys just saw an explanation that the Paul Hewitt had. I'm just going to write this down. He gave you an explanation for this piece, right? The 1/2 AT squared. You guys remember, go to the mine shaft, drop a rock, listen for 5 seconds. It takes 5 seconds to reach the bottom. How far is it falling? Okay. He said, see, 5 seconds squared is 25. Okay. Earth's gravity is 10 meters per second squared. 5 squared times 5. It's about 125 meters. How'd you know that? College. You guys guys just saw that? Okay. Now that's now he, video right prior to that explained where the 1/2 came from. He went through one approach. By the end of class today, I'll show you guys a different perspective of where this comes from. So just take this to be true now, and then by the end of class, you'll see this. Okay. But this is only partial also. This is only true for the condition that you start from rest. So initial velocity is 0 meters per second. So start from rest. Notice how that's consistent with the story of dropping a rock in the mine shaft. That word drop. If you ever read a kinematic motion problem and you see the word drop, it's implied that initial velocity is 0. If you ever see a car brakes to a stop, it's implied that final velocity is 0. So sometimes you have to figure this text, how does this text translate to something, right? Okay, now, there's a reason I dash those boxes, because each of those are part of the story. This is only true for this condition, this is only true for this condition. But what if he'd gone through to that mine shaft and he threw down the rock, okay, so that it started with some velocity? Okay? Turns out all you have to do is add these two parts together. So in general, x is equal to, I'll say initial velocity times time, because now we're about to have acceleration, so we're going to have like a million different velocities, but there's only two that matter, the first one and the last one. In this case, the first one. V naught t, so that's a naught, right? Plus half at squared. Right? So this will be able to field any scenario from starting from rest, not starting from rest, accelerating, not accelerating. Just be able to handle all of that. Okay? Okay, good. Okay. So that's two of these guys. Okay. Now, these two have some things in common, some things not in common. Let's start by the differences. You guys see the top one tells you the speed it can pick up to final velocity, but the one we just put together doesn't say anything about that. Right? The one we just put together tells you how far, right, in meters, but then the first one doesn't say anything about that. Now, what are some things they have in common? They both have the time, tick, tick, tick. They both have acceleration. If that was a non-zero, you could plug in. Right? They both have initial velocity. Right? So I bet you guys can imagine that there are some scenarios that you could get where either of these equations by themselves would not have enough information to solve the problem. Right? Like if I gave you, let's say I gave you the final velocity. Let's say a car brakes to a stop. If a car brakes to a stop, stop, okay, comes to final velocity 0, and I tell you the distance that happens over, right? Or maybe you're solving for distance, but I don't tell you time. That's a common thing. Like if I don't tell you how much time it takes for the car to come to a stop, but maybe I tell you a bunch of other stuff like how fast the car was driving, initial velocity, something like that. Okay. And you might have to use a system of equations to solve these two. You guys remember system of equations from algebra? Okay. And you know what? There actually is there is a solution, system of equation solution to both of those that I'll treat as a third equation. It goes like this. Final velocity squared equals initial velocity squared plus 2ax. Okay. Memorize these three formulas because they will be very useful in this class. They're going to come up over and over all the way to the end. Okay. Now, these are the first three formulas on your AP equations bank also, and you're allowed to use these on the AP exam. Where do I have? Here it is. Okay. You guys see this AP formula page? I gave it the very first day of school. Okay. Now, AP writes them slightly differently. I'll talk about that one day, but you guys see these right here. So you're allowed to access those. You just have to know how to apply them. Okay. Okay. Everybody good so far? Okay. And before I move on, I do want you to at least see that the units check out for this last one, because I don't think it's very intuitive otherwise. But velocity is meters per second. If you square that, don't forget meters squared per second squared. Let me get this in a pinky. So this would be meters squared per second squared. This is also meters squared per second squared. Okay. How about this? Wouldn't this be meters per second squared? That's the acceleration. And then x would be some number of meters, which is also meters squared per second squared, isn't it? Right? Guys, if you add terms together, do the terms have to have the same units? Well, maybe I'll ask the same question a slightly different way. What is 4 miles plus 3 gallons? What is 4 miles plus 3 gallons? What's that equal to? That's not anything. That's silly, right? Yeah. So if you add terms together, they have to have the same units. In this case, they do. Okay, so it all picks up. Okay, picks up. All right, you guys ready to put some graphs together? Graph time. Okay, well, I have to give you a scenario. So here's a scenario. Just very basically, a car drives at constant velocity. And I'm going to define forward as the positive direction. This is probably maybe one of the most basic scenarios I could throw at you guys. So we'll use this to look at some graph ideas, look for some patterns and see how we can expand on these. So draw 3 sets of axes. We're about to do 3 graphs. Later today, we'll do another one of these scenarios. It'll be the same 3 graphs, well, it's the same sets of axes, I should say. Okay. And then tomorrow, we'll do even more graphs for new scenarios. Okay. So we're going to do a bunch of these. Okay. On every single one of these graphs, put time ticking in seconds on the horizontal axis, just like your guys' lab yesterday. So tick, tick, tick. Okay. Going left to right. Tick, 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 tick. Okay. What about the vertical axes? So the first one, do how far in meters. The second one, do how fast in meters per second. And the third one, do acceleration, which is meters per second squared. Right? Meters per second per passing second. That's why it'd be meters per second squared. It's picking up some change of velocity. Okay. Guys good so far? All right. Also, what I'll usually do is I'll start with the middle graph, velocity versus time, because it turns out that these 3 graphs are related to each other. Okay. Actually, there's a calculus relationship. I should even tell you guys. How many guys are taking calculus? Okay. Have you guys started doing derivatives yet or not yet? You started doing them? Okay. Oh, okay. Give you guys a little story here. So usually how calculus is taught is that you're taught derivatives like a hard way, and then you go through and like do the hard way, and then really learn how derivatives work. And then at the end of this process, you're taught a shortcut. So I'll let your calculus teacher take you guys through that story. But by the time you get to the end of this, go back and look at these formulas, because in these graphs, and between these formulas and these graphs, you'll see some things that align with your with calculus. There's a calculus relationship. You're gonna start with the middle one, because the middle one is one step away from the other graphs. You can actually derive the other 2 from the middle one. Okay. So let's go to the scenario. Constant velocity. Hey, is that just the speedometer reading? It's just the same number, constant throughout the road trip? What's that graph gonna look like? Can you guys draw the middle graph before I draw it? So all the time's ticking, ticking along, but your speedometer reading is just staying the same. So isn't that exactly what that middle graph should look like? Right? Constant velocity, cruise control, you're just going with constant velocity. Okay? All right. Let's go to acceleration versus time. Now, acceleration is a rate change of velocity, but if your velocity is constant, then what is the rate change of your velocity? 0. So what does this last graph look like? As time's ticking along, your acceleration is always 0. Did you guys draw it before I got it? Well, this should basically be the axis of what you read. Just 0. Meters per second squared, right? All right, and then finally, let's go back and hit this x versus t. Can you guys draw this graph before I do? You guys have a really good guess what that graph looks like? So say after the first unit of time, you picked up some distance. Then after the second unit of time, you picked up the same amount of distance. So you're continuing forward. And, right? Isn't everything just going to line up on a straight line for constant velocity? Okay. Guys get that? Okay. Any questions so far? Okay. Hopefully that makes sense. Hopefully you're able to digest that even at 10 o'clock in the morning. Okay. I mentioned that these 3 graphs are related to each other. I want to show you guys what the graphical relationship is. Okay. Guys ready for this? Okay. So let's look at the slope of this displacement versus time graph. Okay. Now, that's a constant slope. Right? That's telling you the rate that the slope isn't the slope telling you the rate that you are acquiring distance. Okay? And it would be in some number of meters per second because rise over run. So the slope of this is meters per second. Okay? Hey, you know what else is meters per second? Velocity. Huh. Do you guys think that the slope of x versus t tells you your velocity? It absolutely does. Right. The velocity is the instantaneous rate change of location. So I'm going to say the slope of x versus t tells you the coordinates of v versus t. Okay. So take the slope of the top graph, you can plot the coordinates of the next graph. That's what a derivative in calculus is, by the way. So a derivative is just an instantaneous rate change. So what's the instantaneous rate change of my location? Well, it's my velocity. Okay. Do you think the same pattern applies going from velocity to acceleration? Because I'm looking at these units, meters, meters per second, meters per second per second. I bet it's the same pattern, isn't it? Okay. And what is the slope of any flat line? 0, which is exactly the coordinate of acceleration versus time. Yeah. So that pattern exactly repeats. And I can say the slope of v versus t is the coordinate of a versus t. Makes sense? And you know what? You can actually go the other way too. Let me go from v back to x. Because you guys know that if you know your speed and you know how much time you've been going for, you can figure out how far you've gone. So yeah, you can definitely go from v back to x, right? What graphical property would it be though? Because it's not slope. Okay, slope we did already. Right? Slope will go from top down to bottom. How do you go from the bottom back to the top? Who could figure out what property of the graph? We'll get you there. What property? Who sees it? Yeah, Sam. Huh. How about this? I'll throw in some numbers. Let's see. So tick, 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 tick. Throw some seconds. What if you're going like constant, 5 meters per second? Just come up with a number. 5 meters per second. So like, I don't know, if you're biking around on your bicycle. I don't need no license. So after 1 second, have you picked up to 5 meters? So that'd be 5 meters. After the next second, 10 meters. Then you've gone 15 meters. Then 20. Huh. Hey, 5 seconds for, sorry, 5 meters per second for 1 second. If I multiply those two together, that would give me how far I've gone. Okay? And multiplying them together, isn't that kind of like taking the area of this rectangle? Right? And you know what? If I just expand to the right, I'm just, every single second, it's like I'm just adding on more and more area of rectangles. I see that happening? Right? And let's see, after 4 seconds, 5 meters per second, if I'm 5 times 4 is 20, and the units work out too, because meters per second times seconds gives me meters, it should be 20 meters, and that's exactly 20 meters. Is it? So this has some area with units of meters per second times seconds, right? So based on height, well, height times space, whatever. The seconds cancel, leaves you with meters. Okay. So yeah, you can go from this graph to this graph. The area of v versus t is equal to the coordinates of x versus t. Okay. So area. I should really say the change in coordinate. See the change in, it's like the accumulated coordinate. Because the car didn't necessarily have to start at point 0, but this could slide up or down, but all those would be consistent with this type of velocity. Okay. Do you think the same pattern holds from acceleration back to velocity? It seems like it would, but I hope it does. Yeah, it does. Okay. But guys, what's the area under a 0 curve? The 0, yeah, this is like an infinitely skinny rectangle. There is no area, right? Which means that there's no change in velocity, which means that whatever coordinate you're at, you're just stuck at that coordinate. And it could have been anything. I randomly came up with 5 meters per second, but I could have come up with any speed. It's just not going to change from that speed. Okay? So the area of A versus T tells you the change in B versus T. Oops. guys get that? So that's pretty foundational. Of course, we're gonna come up with new scenarios, but apply the same principles over and over. Yeah.
What's the middle equation?
Oh, this right here?
Yeah.
Okay, yeah, so I was writing out units. This says, it's trying to get the idea of base times height, because a rectangle would just very simply be base times height, right? So this has a height in meters per second and a base in seconds. And I want you guys to see that the seconds cancel, which leaves you with meters. So the area of this represents some number of meters, which would be consistent with this right here. Okay, you guys get that? Okay. Same thing going from here. Meters per second squared times seconds would just be meters per second, so the number of change in meters per second. Okay. And then just to go back, I know I had talked about this before, but the slopes of these things is also consistent in terms of the unit. See, rise over run for x versus t would be some meters per second. Hey, that's meters per second. Okay. And then rise over run to meters per second. Hey, that's meters per second squared. Okay. Remember that because as this class goes on, you guys are going to see many different kinds of graphs. We'll bring in like force graphs and momentum graphs and lots of different kinds of graphs. And you'll see over and over that, hey, there's properties to graphs, there's slopes, there's areas that also have their own meanings. You can figure out what those meanings are if you know how to work units. Okay? Guys good? And then you have to memorize like a tenth as much, because if you know the principle, then you can figure out how everything works. Okay. Probably do oh, we got about 20 minutes. Wow, all right. We are doing fine. All right. You guys ready for a new scenario? We're going to go to the edge of a cliff. Edge of a cliff. And I'm just going to very simply drop a ball from the edge of a cliff. So, drop ball from the edge of a cliff. Then, now I'm also going to say this. I'm going to define down as the positive direction. Now, that's arbitrary. It doesn't really matter. You could define up as positive, but here's what I'm saying is, if you go to the edge of the cliff and you just drop a ball and it moves downward, then if I called up positive and down negative, wouldn't I just have a field of a bunch of negative numbers? And that feels kind of icky. So this is a really common thing to do. Just say down positive, all the numbers are going to be positive. Okay? Let me draw this out. What this could look like. No, we'll do some graphs, but not on this page yet. I'm going to do a table with you guys first, and then we'll go put those graphs together. The same three graphs. Okay. Here's the cliff. Here's you stand at the top edge, and you brought a big old baseball. Yeah. And all you gotta do is just drop the baseball. And maybe I'm from this point of view and I'm taking some photographs. And then you take a photograph every single second. So after the first second, maybe the ball is like right here. So tick. Then after 2 seconds, tick. 3 seconds, tick. 4 seconds. Right. And then at the 4 seconds, it's about to hit the ground. Okay. So tick, 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 tick. Hey, you guys see that baseball's like spreading out? Looks like it's spreading out, doesn't it? That makes sense if it's speeding up, that every successive second is going to go further than the distance before, right? And there's a reason I left a bunch of space over here, because I'm going to put a table together. So we're going to do a 4-column table. In the first column, let's go time in seconds, so variable unit. Next column, let's go acceleration, meters per second squared, then velocity, meters per second, then finally displacement in meters. So variable unit on every single one of those. So like the variable could be displacement, the unit could be meters. Okay. So the time taken along in seconds. Well, the first snapshot is just when this guy's let go of the ball. Okay, so it's like the first nanosecond. So I'll call it time 0, and then after 1 second, maybe it's spelled right there. So 1 second, then 2 seconds, 3 seconds, and then 4 seconds. It's just about to hit the crash and hit the valley below. Okay, see that? Tick, 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 tick. Okay. What's the acceleration of this? Okay. So acceleration of baseball. It looks like it's applied, we're probably on Earth. Sometimes numbers like that are applied. Right when you let go of the ball, is it under the influence of gravity? You just let it go, like one named a second ago. Yeah, and as soon as you let it go, it goes into a state of what's called free fall. And anything that's in free fall is going to accelerate down at 10 meters per second, called 10 meters per second squared. Well, more precisely, it's 9.8, but we'll probably use 10 more often than not. And on AP, you can use 10, and they definitely accept that. In fact, a lot of times they use 10 themselves. To go work for NASA, you probably want to do 9.8. After 1 second, well, it's still free fall. So it's still acquiring speed at a rate of 10 meters per second per second. In fact, after another second, still doing that. After a third second, all the way down, it's picking up 10 meters per second per passing second. Okay? You know what? I might be lying to you guys just a little bit. What possibly important real world factor do you think I'm probably ignoring to simplify this a little bit? Okay, yeah, I'm hearing a few guys saying like wind, like air drag. I'm definitely ignoring that. This is true in a pure vacuum. If you drop a feather in a bowling ball in a pure vacuum, will they fall side by side? Yeah. Okay, now in real life, the faster you go and the wider the object, like air drag starts to build up. We're going to ignore that in this class for the most part. Okay. We have here. How about the velocity? How fast is it picked up to? Now, right as you're letting it go, how fast is it going? Well, 0 meters per second as you're letting it go, because it's starting from rest. Okay, so it hasn't had time to pick up any speed yet. But after 1 second, it's picked up to 10 meters per second, because it's picked up 10 meters per second per passing second. The next second, it's picked up to a speed of 20 meters per second, then 30, then 40. Okay, see how it's picking up 10 meters per second per second? Okay. You know what? That looks a lot like, this table is related to these equations, related to some graphs we're about to draw. Okay, you guys remember this one right here? If you start from rest, do not just zero. This 8 times t, 10 times some tick going along, 10, 20, 30, 40. Okay, and finally, how far has the ball fallen? Now, I've sort of given you a hint already by drawing the baseballs at every single snapshot. See how it's spreading out? I bet this one's a little bit trickier. Okay. But, hey, we have formulas, don't we? Okay. You guys remember like this one right here? Okay. How far has it fallen as a function of time? Okay. No, the very last one that I boxed in does have how far it's fallen, but it doesn't say anything about time, so don't care about that one. Okay. But this one right here. Also, it's starting from rest, right? So doesn't this term just go to 0? In fact, it really boils down to just this part here, doesn't it? It's 1/2 AT squared. Can you see that? Okay. To what is this way? Because you guys are AP, I bet you guys can do 1/2 AT squared, right? Okay. Notes from last class. Okay. So 1/2 a 1 second squared. Okay. I was going to ask you guys what I got, but oops, I just showed you guys all the answers. Okay. So after 1 second, it's fallen 5 meters. You guys get that? Okay. I was going to ask you how far has it fallen after 1 second? And a lot of students want to say 10 meters, but it's not. If you run the equation, it's actually 5 meters. Okay. Okay. Then after another second, it's up to 20 meters. I'm just doing 1/2 AT squared, right? This piece went to 0. Okay. Then after a third second, 45 meters. Then after a fourth second, 80 meters. You guys get it? Okay. So that's the numbers that's on this last column. So it hasn't fallen anywhere after the first, or after, if it hasn't had time to fall yet. Then 5 meters, 20 meters, 45 meters, and 80 meters. And if it's been falling for 5 seconds, we'll put 5 on here. So it's picking up 10 meters per second, that's the acceleration. If it's been doing that for 5 seconds, and you square the 5, 5 times 25, half 10 is 5. It's about 125 meters. Whoa, my voice should sound like Paul Hewitt. Hey, that was the Paul Hewitt story. You remember that? So it had been falling for yet another second to do that. You guys good? Okay. You guys remember taking tables and plotting coordinates so you can make graphs out of those? Okay. There's a bunch of graphs embedded in this data, isn't there? Got acceleration versus time, v versus t, x versus t. I mean, if you're ever stuck and you don't know what a graph looks like, you can always pull up some equations. That's the point I'm trying to make. You can always pull up equations and just start plotting points and see what happens. But let's put those curves together. So same scenario, drop, fall from top edge of cliff. And you can just find down as the positive direction. Drop a ball from the edge of the cliff, down is positive. Okay. Let's make 3 graphs. Same axis as the last scenario, so time is always ticking along in seconds on the horizontal axis. Then the vertical axis, remember it went how far in meters, how fast in meters per second, and the rate change of how fast in meters per second squared. You guys remember that? And so we've got our axes, and tomorrow we'll put together some more graphs that are just different scenarios, see how they play out. I'm also going to start with the middle graph, just like I did with the last ones, and then expand from there. I'll expand to how far is it fallen and what's the rate change of falling. Okay. You know what? I want you guys to, you guys have pencils? Okay. Draw that middle graph in your notes before I do. I'm going to glance around the room real fast. I wonder how many guys can get this middle graph. What's that actually going to look like? Can you figure that out before I show you? Corey got it. Sam got it. Oh, we're not missing somebody. Oh, yeah, Dia got it. Natalie got it. Rich got it. So let's figure this out. Reagan got it. Yeah, Warner, good to go. Isabella got it. Jake got it. JT. And Kristen. All right, so a bunch of you guys got that. Awesome. What you guys came up with, as you said, well, during the first second, it picks up to 10 meters per second. It started at rest, 0, 0. Right. Second goes up to 20, then 30, then 40. Right. It's picking up speed at a constant rate. Looks just like that. 20, 30, 40. Right. Yeah, you guys figured that out. Right. How about acceleration versus time? What's that going to look like? Okay, as soon as you release it, it's in free fall at 10 meters, it's picking up 10 meters per second per second. In fact, isn't it always doing that? If it's always doing that, that's a constant value. So shouldn't that just be, that's what you guys came up with, right? Okay. Remember I was telling you that the slope of V versus T tells you A versus T? You guys know that? Okay, and then, well, I know we haven't done X versus T yet, but eventually it'll connect this way. Okay. And then if you want to go, oops, I see constant slope here. I see 10 meters per second per every passing second. And if you go this way, something to do with areas. So speaking of which, let's look at these two and see if, I'm going to look at this relationship right here. Okay. So time's ticking 1, 2, 3, 4 seconds. Okay. You guys see a rectangle here that's 10 by 1, which brings you up to 10. Okay. Then next rectangle, well, this whole rectangle would be 2 by 10, which is 20. Then 3 by 10, which is 30. Then 4 by 10 is 40. Okay. So see how these areas accumulate coordinates for V versus T? Okay, okay. All right, now we got to figure out X versus T. Okay. Well, let's look at the table, because you can treat these like Cartesian coordinates, right? I just plotted, I started with these two Cartesian coordinates, then I went to these two for Cartesian coordinates. Okay. Now we're about to put these together. Just gonna plot those like x, y coordinates. We've got 0, 0, 1, 5, 220, 345, and 440. So let's do that. We've got to scale this up to, or sorry, so 4 seconds is 80 meters at 4 seconds. Okay. So let's go 0, 20, 40, 60, 80 meters. Okay. 0, 1, 2, 3, 4 seconds. So at time 0 hasn't had time to fall yet. After 1 second, it's fallen 5 meters. 2 seconds, you're up to 20 meters. 3 seconds, up to 45 meters. And 4 seconds, it's fallen 80 meters. Remember, down is positive, so it's fallen down. Hey, what shape is that? That is a parabola. Right? Takes a, that looks like 1/2 AT squared, isn't it? Right? Get your thought. Right? And we're doing right. Last thing I want you guys to see on this page is this relationship right here. See, actually, I'll talk about both of these. Okay. Let's start with this one. Let's start on this one. So if you go left to right, accumulating area under a V versus T graph. This is interesting. It's gonna. Okay. You guys see the area of this little tiny triangle right here? Has a base of 1 and a height of 10, which means it has an area of what? 5. Right? 5 is the number because 1/2 base height, right? 5 is the number. And then what about units? It has some height in meters per second and some base in seconds. So guys, what is meters per second multiplied by seconds? Meters. So this actually has an area of 5 is the number, but it's really 5 meters, isn't it? Hey, that's why you pick up 5 meters here for the coordinate. Is that? What about in general? You guys want to see for let's switch ink color here. Okay. In general, couldn't the base of this triangle be some value t? And the height of this triangle be, well, it'd be v, but is it, in terms of time, isn't it just acceleration times time? Right? In completely general variables. Is it? Okay. And since the area of a triangle is 1/2 base height, the area is 1/2, the base is t, the height is at. You see that? 1/2 base height, 1/2 t at. The t and t can multiply together. So I could call that like 1/2, move the a in front, 1/2 at squared. Hey, 1/2 at squared. Look at that. Remember near the beginning of class today? I told you guys that by the end of class, I tell you another perspective where the 1/2 came from. Thomas delivered. There you go. And then pause you and show you another way if you want to access that video again. Okay. That's good. Okay. And then let's check out these slopes. Now go the slope of x versus t to the coordinates v versus t. This is a little trickier. I'll just do it this way. Okay. Slope has to do with you guys in calculus learned about something called a tangent line. Tangent line. Okay, we're about to use some tangent line. So I'm holding this ruler flush to the curve. Now it turns out at this point, just for this very simple scenario, dropping the ball is kind of like the vertex of the parabola. So my roller would just be flush, has zero slope. Zero slope corresponds to zero coordinates. Okay, zero velocity. But then see as time's ticking along, see that the slope of the tangent line at this point of the curve would be kind of shallow. Then it gets steeper at 2 seconds. And it gets even steeper at 3 seconds. And then, well, 4, okay, so it just keeps getting steeper. Okay, but do you think that the rate that's increasing its slope, do you think that it's increasing at a constant rate? It is. It's picking up 10 meters per second. That's why the coordinates are increasing at a constant rate. Okay? Guys good? All right. So, tomorrow, when you guys come in, we'll do some more graphs and scenarios. We'll look at we'll do for throwing a ball. I'll say upward from the edge of a cliff. We'll do throwing a ball downward. We'll do a car braking to a stop. Right. And if I can, I'd also like to get to some of the problems from this boxy page, the box page problems. All right, so that's some things to look for tomorrow. Who's got any questions?